Hi, good afternoon, everyone, and welcome to this ADVI feature speaker webinar. And today, we've been waiting for this for a long, so we have Professor Corbett Grainger from University of Wisconsin-Madison, where he has been faculty since 2010. His research studies the effect are on the effect of environmental and resource policies on different stakeholders and households, political economy of environmental policies, and distributional impact of market-based environmental and natural resource policies. Professor Grainger is also co-editor at Land Economics, which is one of the reputed journal. He has his PhD in economics from University of California, Santa Barbara. And today, he will be discussing on how fishing activities respond to the marine boundaries based on his research and the data from global fishing. He will explore what fishing the line reveals about the component of regulation and how better designed marine protected areas can improve fishery management. And with this, without further delay, I'd like to pass the floor to Sir.
Thank you very much, and thank you again for the invitation to come. I've been looking forward to this too. I've been looking forward to this because this is the first time that I'm presenting the full version of this, and so really looking forward to feedback. It's something we've been working on for a while. I'll acknowledge my co-authors on this. It's Chris Costello, who's a longtime collaborator from UC Santa Barbara, and then Ben Wolken at MIT. I'll explain the title in a minute. This Pac-Man Goes Fishing, but as Raja explained, what we're looking at here is how the shape of jurisdictional boundaries impacts externalities. And what we're trying to do is use a revealed preference approach, look at where fishing behavior takes place and how it changes with changes in the shape of exclusive economic zones. So I'm going to spend more time than I usually do on theory because the theory really guides the empirical approach here. Typically, I might have a kind of a toy theoretical example that might give some analytical predictions, but I think it's hard to understand what we're doing without going through the full theory here. It's not very complicated, but I think it'll be useful. And then we'll talk about the empirics, where we're using global fishing watch data. So to kind of motivate this, what we're thinking of are externalities that take place over space. And if you look at the literature, you can think of all different types of ways that either externalities take place or there are spillovers over space. I remember in my labor economics class and during my PhD, learning about how people learn in the workplace, peer effects in the workplace. Thinking about that as a function of who you're next to and who's in your sight line, for example. Thinking about air pollution and different types of resources that move over space, like fish and water. Thinking about deforestation and where there might be leakage, and then thinking of wherever there might be policy spillovers that cross jurisdictional boundaries. There's been a lot of good recent work that's been trying to leverage spatial discontinuities, kind of regression discontinuity design, but over space. And a lot of that's been possible because of advances in the types of data that we can use, including what we're going to be doing here today is kind of satellite-based data. So what we're doing here, we have a few questions. The first is how we'll motivate the Pac-Man idea. But what we're looking at here is how does the shape of the boundary impact the externality, the spatial externality? And when we get into the examples, I think this will be a little bit clearer. We're basically thinking about bringing geometry into these models. And then what we're trying to do is use behavior, so reveal preferences. We're looking at fishing behavior on the high seas, and we're trying to estimate, what's the role of convexity or concavity in the shape of these boundaries. And then the ultimate goal of what we're trying to do here is then use this structural model to compare how conservative countries are at managing their natural resources. We're talking about the marine resources, thinking of fisheries. And I say conservative here in quotes because it's really difficult to compare how conservative or how restrictive management of natural resources are when there's so many different tools. So we could use individual property rights, we could use just an overall quota, we could put permits in and have a restricted number of permits, we could put in restrictions on the types of gear, or we could have area closures, we could have all sorts of combinations of those. And when you start looking at that state space, it's really difficult to compare apples to apples. And so that's kind of what's motivating this approach is we're trying to come up with a way to compare all of those different combinations of policies just using the spillovers that we observe. All right. Please interrupt if there are questions, by the way.
Sure.
I'm happy to take them along the way as well as at the end. What we're looking at is high seas fishing. And so what we're looking at is just beyond exclusive economic zones. We could, extensions of this, we could look at the boundaries of exclusive economic zones between two countries. But we're looking at exclusively on the high seas, and we'll kind of explain why we're doing that in a moment. But just beyond 200 nautical miles from a shoreline, sometimes it's closer depending on if there are islands or other things interrupting it. But the idea is if you go 200 nautical miles away from your coastline and there's still ocean, and then that becomes high seas. There are some regional agreements. These are called RFMOs, that's Regional Fisheries Management Organizations, on the high seas. But you could think of high seas as basically being the epitome of open access. Anybody with a boat can go out there and fish, they can catch whatever they want, and they can sell it commercially. So again, beyond the EEZ boundaries, what we're focusing on and what we're thinking about is what types of spillovers do we get from within those exclusive economic zones. All right, so to kind of motivate this, I'm just going to do some really, really simple pictures. And so if we look at this picture on the left side where it's shaded blue, that we're thinking of this as country I's exclusive economic zone. And then on the right-hand side, suppose that's the high seas. So on the left-hand side, only country I's boats or boats that they allow, from other countries, they can do contracting, or else they might not manage well at all and just allow anybody to fish. But they have the right to restrict access to it. Right? On the right-hand side, in that white area, anybody can fish. And so what we're thinking of here is thinking of that shape of that boundary. And if the fish can move back and forth, if they don't know this boundary is here, right? We'd expect, the fish to disperse kind of according to just biological patterns and cross those lines. And as fish move from within that exclusive economic zone to the high seas, then they're moving to a place where anybody in the world could go catch them. So on the linear part of that boundary, that's where I kind of started thinking about this problem, and we did a regression discontinuity design. But when I started kind of zooming in and seeing these weird patterns that you get, we started thinking, if you move from the top of that area, where there's this, the linear boundary, and if you're going right along that boundary, and if you draw a circle around your boat, about half of the water is basically high seas, and about half of the water would be in country I's exclusive economic zone, right? And so if fish are being protected in the EEZ, right, if they're not actively fishing, you'd expect there to be some spillover from that, right? And then as we move down to where that kink in the boundary is, right? If you put the boat right at that pin dot, right, just to the right of that pin dot where they're allowed to fish on the high seas, we're going to say that that's going to be a better place to fish because if you draw a circle around it, more than half of the water is basically privatized there, right? And so we'd expect the spatial externality to be stronger near that kink than at a spot where it's linear, right? If we flip it and do it the other way, put the EEZ on the right-hand side, then it goes the other way, right? The linear boundary is still linear on the top and on the bottom, but where that kink is, we're going to argue that's a worse place to fish than anywhere on this graph, right? Because at that kink, if you go to that pin dot and you draw a circle around it, right, less than half of the water is going to be, privatized, right, or managed by the country, right? All right, so then we take that, another step, right, and make that angle more severe, right? Now this pin dot is going to be worse than anywhere on the previous, or it's going to be worse than the pin dot on the previous slide, right? But the linear areas are going to be the same. Then if you invert it and go the other way, that spot on the high seas is going to be a great place to fish because this is a 90-degree angle and about 3/4 of the water at that pin dot, if you draw a circle around you, is going to be basically privatized, right? It's protected. So this is where Pac-Man comes from, right? So we're thinking of these different shapes, and we think, if you draw this picture, we say, if the high seas is that little triangle, we're going to expect there to be more fishing activity. There's going to be more spatial externalities that should be generated there than if you invert it. And when we've been working on this paper, we call it our Pac-Man paper. It was kind of an ongoing bet whether anybody would dare call it the Pac-Man paper in a seminar. I'm the first one presenting it, so you're taking advantage in doing it. Right? So this is basically the thought experiment, right? And real world boundaries are going to be messier. They're not going to have these, for the most part, they're not going to have these kinks, but they're going to be these long functions or long kind of smooth continuous functions. There are going to be some kinks that we'll deal with, but the whole idea is we're going to be moving along these high seas boundaries all around the world, thinking, is this going to be, more or less, a Pac-Man or kind of an inverted Pac-Man setting, and then looking to see if the actual fishing activity correlates with that. To motivate this one, when I first started thinking about this, I had it set up, and there were about 1,000 local regression discontinuities that I estimated. Right, so I went around the world and chunked up these EEZ high seas boundaries, and just looked at the running variable on the horizontal axis there as meters, right? And so you move out to about 40 kilometers to the left. There you're inside of Japan's EEZ, and then as you move to the right-hand side, you're on the high seas. And what we see is there's this jump in fishing activity when you cross that boundary. And there are a lot of, I didn't put them all in here, there's too many examples, but Japan is known for doing a pretty good job of managing its marine resources. There are a lot of other countries where that line would be flat, right, where there's no jump, and that kind of indicates that people don't think that that's a well-managed resource, I guess is what that might indicate. So there's the jump that we're interested in, but also the slope, right? And that slope is something that is difficult to get at when we're looking at both on the inside and outside. There are different things that might pressure fishers inside to move outside, right? Area closures, seasonal closures might push a Japanese fisher from the inside to the outside. And so comparing these gaps in a bunch of kind of reduced form RD, it made it difficult for us to say anything about whether Japan was more conservative than Norway or Chile or Peru or all these others. So we ended up moving to a structural model. So one more example, a very small island, which is almost impossible to see. That island up kind of north of Iceland off of the Norwegian coast. This is Jan Mayen. This turns out to be another good place to fish. So this is on the left-hand side, that's the exclusive economic zone going on about 100 kilometers. And then as you move to the right-hand side, there's this big jump in fishing effort that kind of falls off slightly, but it's still, there's still quite a big spatial spillover we expect, even 100 kilometers away from the boundary. All right, so we moved from kind of this reduced form world with a bunch of RDs that were difficult to interpret to what we're talking about today, where we're thinking more carefully about the shape of the boundaries. So those RD plots don't tell us anything about the shape of the boundaries. This image here shows these are the EEZs kind of within these bubbles down in the Pacific. That's Australia to the left. And you end up with these kind of funny shapes, right? There's some bubbles. The perfect circles are very small islands in the exclusive economic zone surrounding it. But the areas inside of those cloud shapes are actually they're little chunks of high seas, right? And so, and there's interesting geometry even within those. And so what we're trying to do is move around these more complicated shapes and say, can we do something beyond just a linear RD where we're thinking, are we inside or outside? Instead, we're also trying to say, are we mostly surrounded by an EEZ, or are we mostly surrounded by high seas, conditional on being on the high seas? So as we're thinking about this and trying to make these comparisons, the way we're describing it is thinking that some countries are kind of endowed with good shapes, and others might be endowed with kind of bad shapes in terms of if your goal is to keep in your resources or if your goal is to, generate externalities. That's also true if you're setting up a marine protected area, and that's one of the ways we're thinking about this. If you put a marine protected area within your EEZ, the shape and the location should matter, right? And it matters what your goal is. If your goal is just conservation, and if you don't want to generate externalities, that gives you a very different shape than one where you might be interested in generating some externalities by closing off fishing to some other spots, right? Using the structural approach that we're going to be going through here today, that also allows us to provide a ranking. That's something that we've been interested in without thinking about each specific management tool, because again, in a regression framework, we just can't control for them all. There's too many different combinations. All right, so the motivation for this, I'm going to walk through a model. This is Marty Weitzman's paper of prices versus quantities in fisheries paper that is not as well known as just general prices versus quantities paper. If you studied environmental economics, you probably heard that prices versus quantities. That's basically saying under what conditions is it better to regulate emissions with a tax versus a quantity instrument where you restrict the quantity, right? It's a beautiful theory. He also did the same approach in fisheries. And so we're going to start with that. But what we're trying to do is add space in the simplest way that we can do it. Right. So we're going to start with Weitzman, and it's going to be discrete time, and it's just a single location commons model. And then we're just going to extend that to discrete space, and that's the way that we're going to treat this empirically. We're just going to have patches. And you hear patch, think pixel, right? Because when I get to the satellite data, it's going to be pixels. The key assumption that we're going to have kind of moving through this is that fishermen know their marginal harvest costs within a period, and we're not going to be going through the dynamics. Our empirical application is just 1 year. We're not thinking about dynamics. We're thinking of this, basically an equilibrium. The goal here is when we extend to end patches, we're trying to connect the regulation in one patch to effort nearby, right? So when I say effort, it's how many hours you spent fishing. But the idea is, think of the regulation that might be taking place within one patch. If we know that these are interconnected through fish being able to swim and move over space, right? Also dispersal of larvae and other things. That interconnectedness allows us to take a structural approach as long as you buy the assumptions that I'll go through in a minute. Okay. So for each patch I in a given period, the stock is going to start at xi, and then we can harvest off h, and then the escapement is just how much residual you allow at the end. Right? So that's how many fish you allow to escape. That's where that term comes from. It's just the difference between how much you harvest and what the starting stock is. We're going to assume the price is constant on the high seas when we're talking about tuna fisheries. I think thinking of these fishers as price takers is reasonable. But the key insight here is that within the period, the stock is driven down. And so the marginal extraction cost rises as the stock is depleted, and that's within a period. Most of the fisheries economics literature they might just take a discrete T, but each T is a season, right? And they move one season to the next and keep track of the stock. His insight here is as you're depleting the stock within a season, you're going to have rising marginal costs. And this is basically a stock effect. So as you extract more, it's harder to find the next fish. All right. So we're going to have a marginal cost that's patch dependent, or we're going to allow it to be patch dependent. And that is going to depend on the current stock. And then we just impose some regularity assumptions on this. First one basically just says is you have more fish available, you're going to have a lower marginal cost of harvesting it. And then the second condition is that, as that stock goes to zero, it's not profitable anymore to extract. So a convenient functional form, and one that's common in the literature, is just scaling, taking some parameter and scaling it, dividing by S, the stock. So this captures that stock effect at low S, at extremely low S, and then this allows for heterogeneity between patches. So this is also this is going to be useful when we take this to estimation. So period T profits in patch I, it's just revenues minus your costs. And we're just integrating over the costs as we move from that starting stock to the amount that's left over after we harvest. Again, the P is fixed, and then Y again is the escapement goal. Right, so we're assuming that fishermen are myopic here. We're not thinking about dynamics between periods. So they're responding only to period T incentives, and this is going to follow Weitzman's basic model. We're going to then introduce a per unit harvest price, tau. I'll just stop and note, this is extremely unusual in fisheries to have an actual tax on harvest. There are a few places that do it. So when we're going through this, you could just think of this as a proxy for some type of regulation that makes fishing more expensive. All right. So given some per unit harvest charge, you could think of that as a harvest tax, but also some policy that makes it more expensive to catch. What fishermen are trying to do is maximize this escapement. They're choosing escapement, since escapement is just your starting stock minus your harvest. That's equivalent to just choosing harvest. And all we've done is just taken the revenue minus the costs, and then that last item is the economic incentive, adding that tax. So what we're doing is shifting that tax up or down. And again, you can think of that as the stringency of the regulation, which would also just increase the cost of harvest. All right, so the pretty little drawing that we made up, and this is the idea. So the cost function would be the blue line. The price P is fixed. That's the horizontal line at the top. And then on the horizontal axis, we have the stock. And the idea, again, is we start at X. That's the beginning of the period stock. And then as we harvest down the stock, we're moving toward Y, right? And then at the end of the period, Y is where we end up. And so if we put in a tax, right, that's going to be kind of shifting up or down what that line looks like. And then that also gives you kind of indirectly what your escapement is going to be. Okay? So if you're charging more, you're going to have a different escapement than if you basically set a tax equal to zero. We have the tax revenue on there, but then we have the individual firms' profits. Right? So again, the C could be patch specific. The tax is just moving the stock, why we end up with it within a season. So how much escapement we have. And escapement is going to be kind of a critical thing here, because escapement, you can imagine some of these fish escape harvest and stay within the exclusive economic zone. Some of them escape and swim across that boundary and end up in the high seas. Right. All right. So we can think of tau here. This is the patch-specific regulation. Again, Weitzman's motivation here, he thought of this as a tax, but we're not going to take a stance on what exactly the policy is. We're just thinking this is some proxy for how stringent the regulation is. All right. So made up of the first order condition and then this escapement rule. So the first order condition is kind of clear, right? This is not a complicated maximization problem. especially we put these regularity conditions on the sea and so on, we assume that cost function, the marginal cost function, and that tax or whatever the regulation is, those costs are known to all agents, and this gives us a unique equilibrium escapement in each patch. So basically, if we take that marginal cost function and invert it to find V that way, then we get a closed form solution for what our escapement's going to be given tau. Right. So far, this is just Weitzman's paper, and I've added an I to it, okay? Now what we're going to do is connect the patches. Okay. So escapement's going to depend on P and tau. Again, we're abstracting away from time. We're not thinking about what happens following period. We're thinking of this as equilibrium. So within a patch, we have an equilibrium escapement that's constant over time. And so you could think of this as if you have tighter regulations, you're going to have higher escapement, more fish are going to be left in the ocean, and some of those fish are going to swim across boundaries. All right. Now, if we start introducing time here, and this we only need this for the growth function so that we can make the connection between patches. So if we think of what's the starting stock next period, and so we have the escapement, and then that's going to give us our starting stock next period. Once we account for the growth in the stock, there's going to be some natural mortality, but there also is going to be some natural reproduction from the fish. So that G is just the growth function. It's increasing in concave. And then D, you could think of this as like a source receptor matrix. Right? It tells us the connection, how much movement, how much biomass do we get from patch J that ends up in patch I next period. Right? Right. Since we're analyzing this at equilibrium, YJT is the same as YJ. We don't need that T, like I said before, right? That T was just a temporary placeholder to show you that the growth function matters. And so XI then, we can write down XI is just this function over J, so that DJI again is the source receptor matrix basically. And so all of the patches that are connected to I are going to be included in this D matrix. So the stock in patch I is going to depend on the stock in all of those other J patches. And as such, it's going to depend on all of those incentives or the regulations in all of the connected patches. And so if you have strong connectivity between my patch on the high seas where I might want to go fishing and your patch where you're regulating and doing a good job of restricting harvest, if there's really strong connectivity, then that means that I'm going to end up with more fish from you because of tau. All right? We're going to expect that the distance is going to matter. We're going to explicitly bring that in. So farther patches matter less when DJI is small. And what this is going to do, and when we go and grid up the ocean, this is going to allow us to think about cross-jurisdictional spillovers. Does that make sense so far? Okay. So this is going to matter empirically because what we're trying to do is infer the regulation stringency, kind of think about, again, tau j as being a stringency, not necessarily a tax, but we're trying to infer that from observed fishing patterns on the high seas. So we're not looking at the fishing where the regulation takes place, we're thinking of the fishing where there's spillovers onto the high seas. So the spatial equilibrium gives us a mapping, right? From this vector of tau, the stringency variable, to the x's, which is the starting stock within a period. And the trick and the challenge that we have with the satellite data is we don't know the stock, right? Satellite data do a lot of good things, but they don't count how many fish are under the water, right? So all we observe are proxies for harvest. We actually observe effort. There are some places where we can translate the effort into harvest, and there are other papers where I've worked on the same data where we do that. I'm just going to show you how we make that connection. But what we're going to be doing empirically is just looking at the effort as the output variable. But if you assume the standard relationship, it's just a hop, skip, and a jump from the stock to actual harvest. If you assume that harvest is basically a function of effort on your patch and your starting stock. So E here is the fishing effort. You can think of this as being measured in hours, how much time you spend fishing in a patch. And then we can take that and rearrange, and we see that effort is going to be increasing as escapement falls relative to the startings. So again, Y is how much fish you want to leave unharmed at the end of the period. X is how much you start with at the beginning. So this allows us to connect what we're observing with the behavior, which is effort, directly to the regulation. And again, we're not going to say that we know what those regulations are. We're just trying to infer it based on fishing behavior. So in equilibrium, we can say something, if we can say something about the relationship between harvest and the stock through effort, if we can make that claim, then we can make the substitution where we had Y was a function basically of the price, the difference between the price and that tax, right? And so if we take that, make that substitution, what we've done now is substituted within that growth function, that's basically the biological growth function, substitute in these economic variables in for Y. We're summing up over all of these DJIs, right? Summing over J. And what we're interested in is summing up over all of the interconnected patches so that we can say something about what we expect effort to be. So if we start with that relationship between the stock and escapement, which is a function of your economic variables, then we can get to this effort equation. And this looks a little bit messy, but this all we've done is just substituted everything we've built up on here until now. And so what we observe in the satellite data is going to be EI. And so we're going to grid the oceans. We're going to observe how much fishing effort takes place in each of our small grid cells. We're just summing over the year. We're not taking into account dynamics and these other things. We're trying to do this as simply as we can. And it still turns out to be, it gets complicated, even trying to keep it relatively simple. All right, so we're going to parameterize, the next thing we're going to do is parameterize that DJI and that BI. And then our goal here again is to recover these dispersal parameters and then recover basically tau. And when we say tau, you can think of this as kind of a ranking of how stringent different countries are with their regulation. All right, just gonna have a drink quick. So the Pac-Man thought experiment that we have here is, how does the fraction regulated, so if you draw a circle around the center of the small pixel, right? Those pictures that we had before, if you do that and then you just repeat for all of the pixels that we have, how does the fraction within that circle that's regulated, so that intersects an EEZ, how does that affect the effort that we observe on the high seas? And again, we're only looking at the effort on the high seas here. We're throwing out some of the other data. And then what we're going to do is see if we can separately identify dispersal, these functions of space basically, and then the stringency of the overall regulation. So to fix dots, we're going to pick some high seas patch, pick patch I, and then this is going to be connected to many patches nearby, and we expect that importance of that connection to go down as you move further and further away. In principle, it's possible that if you pick a patch just off the coast here in Japan that is connected to something that's happening off the coast of Florida, right? but you'd expect that relationship to be really small, right? So what we're doing is looking within 100 kilometers is our baseline specification and seeing what happens if we expand that. But we're trying to look somewhat locally, and that 100 kilometers was guided by what the fisheries ecology literature would say to start with. All right, so we're going to fix patch I. It's connected to a lot of patches J. Some of those patches are going to be on the high seas, and some of them are going to be in regulated EEZs, right? And sometimes it's going to be multiple EEZs that are close by. So we're going to keep track of all those things. Right, so just for exposition, if we assume that these cost functions are the same across patches, we don't need that, but just for writing this down, then we can get this equilibrium stock in the high seas patch I. It's going to be a function of all of the stocks J in that first summation that are in the high seas. HS is high seas. It's a slight abuse of notation here. I'm sorry that I used J multiple times, different summations. Should change that. The second one, we're summing over some region 1, right? So that's another EEZ that's close by. We could have region 2, we could have region 3. In some places, it gets kind of funky and there are many EEZs nearby. Most of them, it's going to be 1. Right, so each jurisdiction is going to contribute some stock, some biomass to patch I through dispersal. This is just, just movement of the stock. And then the contributions are going to depend on the regulation in that jurisdiction and the distance. So we're going to then define a jurisdiction level stock production parameter. So when I say jurisdiction, this is like an EEZ, and we're separating territories from the mother country in the cases where we have that. So it's kind of the local EEZ. And so we're going to define this theta as going to be some function of that tau. It's, that B function, if we're assuming the cost functions are the same everywhere, that B function is going to be the same everywhere, and P is the global price, right? So we're going to have this monotonicity again. Tighter regulation means more stock is being produced. And this allows us to kind of summarize the regulation stringency in a reduced form. I'm almost to the data, I promise. Now the stock is going to be, we're going to think of this as kind of exposure times production. When I say exposure, you can think of that as how close by you are, and then how productive an area is. And so how much stock jurisdiction K is going to be producing, that's going to be theta K. And DJI is as it was before. That's kind of how exposed you are in patch I to all these different patches K. And so the difference between what we had before and now is we have these thetas in front of these summations. So each of these thetas is going to be EEZ specific. And this is going to be what we're going to be recovering when we're estimating this. Now we're going to add distance. Again, you'd expect the effect of a faraway patch to be smaller than the effect of what's happening close by. And so we're doing this just with a quadratic dispersal kernel. And so we're saying that DJI, again, the effect of patch J on patch I is going to be alpha plus this beta times DJI plus this quadratic term, this quadratic distance squared. So DJI is just the Euclidean distance, and then alpha, beta, and gamma here are capturing the dispersal and how it decays with distance. Okay, so for each pixel I in jurisdiction K, we're going to take the area that is within K if we draw a circle around patch I. Okay. And then W, you could think of this as integrating over, all of the patches within some radius. And then Z is the same thing, except it's the distance squared term. So delta I, which is a function of J here, is just the distance from point J to patch up. Here's a toy example. I like toy examples. On the left-hand side, we're going to say this is the high seas, that pink area. And then we have two jurisdictions colored blue and green. Each one of these pixels is going to come from the data. And so if we look at that top circle, the circle to the farthest left, we're drawing a circle around that center pixel's centroid. And then that circle is going to have some fixed radius. I'm not going to show all the results there. It's just going to pick a radius of 100 kilometers. But here, if we do this, that's going to intersect two different EEZs. You can see that pixel is adjacent to the green EEZ, jurisdiction J, right? But it also, if we fix that radius, it intersects a little bit with that whatever's happening in that blue jurisdiction. Then you can imagine doing the same thing over and over and over again with all of the high seas pixels. That's basically the data that we're using. All right. So
how large is the area that is represented by each pixel?
In this picture, this doesn't map very well to the data. Yeah, this is, I'm just trying to make something relatively small. In the version I'm showing today, the data are at about a 25 square kilometer grid. Yeah, per pixel. Yep, yeah, 5 by 5. So we're using A, W, and Z. These are our exposures. A is going to be the exposure, the proportion of that circle that intersects with the different areas, right? So since we're on the high seas, part of that circle will always intersect the high seas. But part of the circle could intersect nearby other jurisdictions, right? EEZs. And so that A is the fraction of the circle intersecting high seas. And in the middle part, it's intersecting area 1 or EEZ1. The second one is intersecting with EEZ2 and so on and so forth. Right? W then is going to be kind of the weighting by distance for each of these areas nearby, and Z is the square term. So what this does is this allows us to separate the regulation through, when I say regulation, that's these data parameters that are in front from the dispersal, alpha, beta, and gamma. So for each eye, the total area or exposure is fixed. Right? We're looking within some fixed radius. And so if we sum up over K, we're going to have some constant, AIK, and WI is going to be some constant if we sum up over K. Same thing for Z, right? So what we're going to do is omit the high C's. It's going to be our baseline category. And so everything's going to be kind of relative to what the fishing on the high C's will look like. Again, that's unregulated area. This is going to be identified as long as we have at least a couple of EEZs. Right? So we have N jurisdictions. We have 3 primary parameters. It's basically that N plus 3. But this exposure is going to generate 3N distinct sources of variation. Okay, so as long as N is greater than 1.5, right, N is going to have to be an integer, so it's going to be greater than 2, then we're going to be able to identify this. So we're going to have multiple moments that pin down the same parameters. And I'll stop and say, I am not a structural person. I grew up in a very reduced form world. When I say grew up, my PhD was a very reduced form world. And this is my first kind of foray into structural econometrics. Thankfully, Ben Olken, the co-author here, knows this stuff inside out. So it's been my chance to learn some structural econometrics. Right, so empirically, what we can do is exploit this, and we're going to be able to separately identify this vector of theta k's, that's the stringency for country K, and then this dispersal function, alpha, beta, gamma. Go to the data. The data come from Global Fishing Watch. This is being used increasingly and anybody studying the ocean, I've a few papers using it. It's great. There's public use version available on their website that's actually quite good. And if you write a proposal, those of you interested in this, you can write a proposal to get access to the more restricted version. The restricted version tells you a lot of details about the vessel, hull number, the flag that they fly, and other things. And so I've used that in other applications. Here, we're not interested in where the boats are from, at least not yet. So we're just using the total effort within an area. So what the Global Fishing Watch does is this uses navigation. This is a precursor basically to GPS, AIS. And this is navigation equipment that boats on the high seas should have. Not all of them do. If you're interested in this, I'm happy offline to send you some papers that try to see exactly where those boats are from and how, where we might be underestimating fishing. Some boats turn off their navigation equipment to fly under the radar and not be detected fishing places where they're not supposed to. And then there are others that, for whatever reason, go dark for periods of time. AIS, basically what this does is every 5 seconds or so, it sends a ping to a satellite, and this is just for navigation. It tells you, am I going to run into a boat or not, right? So most of the time on the high seas, you're not going to run into a boat. But if you look at this picture, you can see the major shipping routes, right? So it's called Global Fishing Watch, but this is all ocean-going vessels. Any boat that is going, a few miles offshore should have this technology on board. All right, so we see where all these boats are. This is for 2015. This is the average number of vessels, per unit area. What we're interested in is fishing effort. So we're going to use the Global Fishing Watch data that uses AIS and a machine learning algorithm to predict fishing. This was I probably should have put the slide in that describes this a little bit more, but this was an effort. Leonardo DiCaprio helped fund it, and Google has done a lot of the heavy lifting and hosting the data. Global Fishing Watch now it's a pretty large organization dedicated to protecting the oceans. Basically, what this does is this takes this AIS data, which is just track level data from an individual vessel, so you can follow it over time. It's pinging the satellite really regularly, and the idea is, if we look at each of these red dots, which are difficult to see on the screen, but that's an individual ping that they're using, right? And if you look at the distance between those, then that tells you how far they've gone between pings. And then you can look at the shape that they're drawing out. And so on the right-hand side, this is the easiest one to describe. That's a purse seiner. If the boat slows down and draws a circle, and then it stops, that's most likely a purse seiner. It's a kind of an all-encompassing net that cinches and basically pulls everything up with a crane, everything that's in that vertical column. It does not discriminate, right? It catches everything that's in that path, including sea turtles and dolphins and all sorts of other things. Second, the middle one is long line, right? So long line is, they're out catching, it's usually tuna and billfish in our application. And then on the left is trawling. Trawling is also something that we worry about, especially dredge trawling, because this is also indiscriminate, throws out basically a big mesh chain link fence, right? And just catches everything that it encounters as it drags along. And they can do that along the bottom of the ocean. And it's very destructive if they're going on the bottom. You can also trawl further up in the column. There are different types of trawl, but the trawl path looks like the picture in the top left, right? So we know the type of gear that they're using as well as how much time they're spending fishing. We use the same adjustment that Global Fishing Watch does, and we end up with just an estimate of total fishing effort within a pixel. All right. So we're throwing out areas that are inside of exclusive economic zones. We're not using the data there, at least yet. And then we're throwing out data that are on the high seas, but really far away from, EEZs, because what we're trying to pick up here is spatial spillovers from the EEZs. Right? So again, if you go far enough away, you'd expect that impact to be minimal or zero. So we're looking within about 100 kilometers in the main specification away from the EEZ boundary, and so that gives us these areas that are kind of highlighted here. The blue lines here denote the EEZ boundaries. Okay. And what we're looking at is only the intersection of the EEZ and the high seas. We've thought a lot about looking at EEZ to EEZ boundaries, and I think that might be the next thing that we try to tackle, but gets much more complicated when you start thinking about some area that is not unregulated. Having the baseline be unregulated here makes it much easier for us. So the way we draw this up is, again, this is Pac-Man again. And so, again, the way to think about this is that Pac-Man shape. I'm drawing these circles, and then I'm drawing the circles and moving around and redrawing the circles and doing that for different ones, right? And so the way to think about this is if we start along that boundary in the picture that we showed before, where we have that 210-degree angle, right? We have country I's exclusive economic zone on the left, high seas on the right, and we're going to argue that that dot in the middle of that colored circle, of a half-colored circle, is going to be a good place to fish because more than half of the area nearby is protected or at least regulated, right? So we move away from that exclusive economic zone boundary onto the high seas. That area overlap is going to go away, right? And that's the variation that we're going to be trying to exploit. You also get movement as you move north or south on this map. It's not just moving away from that kink, right? So that area that intersects the exclusive economic zone is what we're interested in. Tried to pull some pretty pictures, so this gives you a sense of individual pixels and kind of the scale here. So the inner circle is 20-kilometer radius. We're not using that, that's too fine. The specifications I'm going to show today are using the 100-kilometer radius, and then you can also go 200 kilometers, go further and further. Our results are super robust so far to going further away. Going really close within 20 kilometers, there's not much variation to exploit, right? You can't pick up these changes in the shape of the boundaries with such a small radius. So we're showing that the 100 specification because it seems to be that sweet spot where you can pick up kind of changes in convexity and concavity as you move along these boundaries. Right, so these are real world boundaries. That one in the middle, we're going to be intersecting, at least for some of those pixels, multiple EPZs, but one is on the left and one is on the right. Right? Sometimes they're going to be both on the left-hand side, both on the right-hand side, but we're moving along where a country's jurisdiction changes from one to another, or the jurisdiction of the ocean changes from one to another. Right. So the shapes of these, sometimes they're very straight and boring, right? And sometimes there's a lot of within country variation. That within country variation is what allows us to identify this. And so at the end, when I show some of these estimates for the countries, some of these theta parameters are pretty hard to identify because the boundaries they're either a very small island with a perfect circle. It's kind of hard to pick something up there. It's harder than these interesting ones. Or if it just has a long straight boundary or a kind of constant curvature. Some of them are harder to identify. All right. So we have the same I index. This is an index, high seas pixels only. And then what we're doing is keeping track of EEZs that are within 100 kilometers of the center of pixel I. We have fishing effort as our outcome variable. And so that's going to be observed for each pixel I on the high seas. And then we have AIK, that's the exposure of the area of the circle drawn around the center of pixel I that intersects EEZ. Okay? So it's the area of the circle, that's A. W is taking into account distance, and Z is distance squared. So what we're going to assume here, and what I'm showing is we're assuming that these alpha, beta, and gamma are the same everywhere in the world. I'll say that's a strong assumption that the dispersal, in the tropics and the South Pacific is kind of the same as it would be outside of Iceland. We have done it and estimated it locally, but in the end, what we want is to be able to compare the thetas. And so we need to take some stance on what happens with these slope coefficients, because the thetas enter multiplicative, right? And so what I'm going to show today is we're assuming that they're the same. And then the thetas here, these are these EEZ specific intensities that we're interested in. What time do we end?
As we have 1 hour, we are actually.
We're very close. Okay, perfect. So we're doing this with Poisson regression. We're doing this with Poisson regression because we have a lot of zeros. So paper by Chen and Roth that talks about this. Doing it with Poisson regression. And the beautiful thing here is everything enters multiplicatively, and this matches really closely to the model that we started off with, right? The cool thing here is, since it's Poisson and it's a structural model, we don't have to do GMM. I tried GMM, didn't work very well. It's hard to get this thing to converge because we're trying to estimate it globally. But we have individual EEZ fixed effects, and then coded up the Poisson maximum likelihood, and voila, here we are. Just going to show really quick what happens as you move away for different shapes. That pink line is Pac-Man. That's the Pac-Man that we showed before. There's going to be more fishing near that boundary where it's Pac-Man than the inverse Pac-Man, which is the bottom line. Those are the predictions. And then the linear coastline is the one in between. So this comes from the estimation using Poisson regression. I'm going to show really quickly the thetas tend to make sense when we look at what the rankings look like. One thing that jumped off the page to me was the theta for Palau is toward the bottom of the rankings globally. And that was very counterintuitive because Palau is known for being very good at managing its resources. But it's because so far we aren't taking into account the MPAs. So that's going to be the next step. This shows the fishing within Palau is that bottom kind of trapezoid shape, but high seas fishing is the green areas elsewhere. If you look at the shape of Palau's EEZ, the area where it's shaded yellow here is the domestic fishing area. That's exactly the area that we see domestic fishing. Everywhere else is a Palau National Marine Sanctuary, and so if you look at where fishing on the high seas takes place adjacent to the MPA, which is exactly what we'd expect. But overall, Palau doesn't have a lot of fishing next to it because it's so good to fish next to the MPA that they don't fish next to the place where they allow domestic fishing. All right. So we estimate this with Poisson, maximum likelihood. Here are the parameters that you probably don't care so much about, alpha, beta, gamma, but this allows us to identify these thetas. These are the thetas in ascending order. Just going to note, what we have up to the right is Argentina is a very good place according to our model. Some of the others that jump out, Peru, Norway, some of these I think are quite intuitive. India was a surprise to me, and it's something that we're looking into. But I think the next step that we have is to go in and control for these spatial regulations, see if there's something going on. All right, I'm going to stop there, knowing that I'm already over time.
Thank you so much, Mr. Grainger. So is there any question from this person?
Yeah, please.
What I was wondering is that, you looked at those fishing, but one of the things is that when you have this curve, right, what you call pattern.
Yep.
So in those kind of pattern situations, I think the fishing should be low because of overharvest. That's what I feel. But you are saying otherwise, right?
Because of overharvest. Okay, so this is so in equilibrium, we're expecting if the area is well regulated in the Pac-Man area, right? And if you have this small kind of kinked area that comes in, if it's well regulated here, every year you're going to get some spillover, right? And so every year you'd expect some fishing to pile up there, right?
So did you control for the regulation?
So we're not controlling for the regulation. The idea is that we're trying to back out how conservative the country's regulations are from these estimated parameters.
Then you talked about allowed.
Yeah.
My problem is that I don't know which share data you took, like maybe time series, right?
Oh, we're just doing it with a cross section right
Okay.
now.
The thing is that if you look at particularly the Pacific Island countries because of over harvest of tuna,
Yep.
like there's so much demand. And then what's happening there is that they have now moved into what you call the quota system.
Okay.
So some of those systems that's implemented by different countries have changed the fishing behavior and the overharvest, right? So I don't know, maybe controlling those kind of scenarios across the globe, maybe you'll find different results.
Yeah, we've talked about that and trying to leverage places where the problem is there are a lot of countries where we don't know exactly what the regulations or what the combination of the regulations are, or if they're enforced. Because the enforcement is another dimension. There are some places that on paper have very stringent regulations, but they don't even restrict foreign vessels from coming in, right? They often just lack the capacity for enforcement.
So did you categorize the fish by different type, or you just have all fish in one basket?
We can't see what the harvest is, but on the high seas, about over 90% of this is tuna and billfish. Based on the countries that report the landings.
And also, like, there are different kind of within tunas also, like.
Sure. Yeah.
The demands are varied.
Yeah.
So,
But the idea is in equilibrium, right? Assume the countries haven't changed policies much from one year to the next, right? In equilibrium, you'd expect this to be reflecting how profitable it is to fish here versus somewhere else, right? If it could be that you could go after a high value species, southern bluefin tuna, something that's been overfished and is hard to encounter. You might fish for days and pick up only one if you're lucky, right? But it's very valuable when you go sell it in Tokyo, right? There are others that you're going to encounter more of them and you're going to spend less time catching more fish. But in equilibrium, we wouldn't expect there to be, big gains from changing your behavior. Otherwise, we'd expect the fishing to shift from one place to another.
my other problem is that different countries are highly economic and rich, poor, so the power to implement the regulations
Yeah.
varying, right?
Yep.
And also the size of fishing vessels that this country have.
Yep.
So we don't account for it.
On the high seas, anybody can go fish, right? We're not looking at the fishing on the inside of the boundaries. I 100% agree that that what happens inside some of the countries, they don't have the capacity, they don't have the means to enforce what's happening on the inside. And so that's one of the reasons that we're not looking at the regulations themselves. Because some countries have, on paper, stringent regulations, but they don't keep out, vessels from overseas that come in, fish, and leave, right? So that's the reason that we're not trying to control for the regulations, is because knowing how well it's enforced and knowing all these other things, that's a really high information requirement. I am interested in ways to improve enforcement of the regulations, and we've been talking to some groups in the Pacific Islands region about this. And yeah, it's ongoing, so I probably shouldn't talk about it on a webinar. But that's something that we're interested in, and they were very motivated by exactly these types of pictures that along their exclusive economic zone, when they are enforcing, and keeping fishing out, that there is this fishing the line activity by foreign vessels. Is something that, that concerns them, right? Because that also has a negative externality back on the protected area if what you care about is species diversity or something.
And also, because cross-sectional is cross-sectional, right? But if you have looked into MPs, because sometimes some countries implement policies that different.
Yeah, and we do have the MPA maps and when they've been implemented, and then my co-author Chris has a recent paper that looks at the effectiveness of some of the MPs. Some of them are basically paper parks and they're not really protected at all. Some of them are very effective, and so we do have that. And so one thing that we could do is go back to 2015 when the global fishing launch data starts. I think it was 2015, and then move forward and then take into account these changes in these and see how that shifts the relative thetas. That's on the to-do, but just doing it for 1 year, running this on my machine, one round takes about 2.5 days. And so we've been just trying to get this one thing to converge. Once we kind of settle on the specification that works and code that works, and that's what we've talked about is bringing in the panel dimension where some policies are changing, especially protected areas, because that's something that we can observe. Yeah, thank you very much. It was very useful.
Yeah, as we have already run out of the time, it is like 1 hour, which is pretty, but I think we can still have the conversation later. So we will be around here for a while.